right, cool.
All right, welcome back. And we'll have two talks back to back by Mike and then Clay. And after the talks, we have a break at 3:15. Thank you.
All right.
Welcome back. So this is a little bit of a shift of emphasis relative to where I've been in the last couple of talks. Not so much about forecasting. Another example of decouple, recouple, and also an example of what I'll call Bayesian emulation, which allows you, it's a way of thinking that allows you to exploit simple models, in this case decoupled simple univariate models, to explore and interrogate more complicated models. Okay? And that's a concept that is not specific to this area, but it's a nice example. And it's different in the sense that this is data of counts. So it's not being primarily focused on forecasting, it's more focused on monitoring. And so the models, dynamic models, are not conditionally Gaussian and they're not conditionally linear. Okay? So let's see what we've got here. So it's about traffic flows on a network. A given network is defined collections of nodes, where in principle any node can communicate with any other node. The example is web traffic in a set of domains in a particular website. And the interest is purely initially exploratory, but these models are now being developed and scaled up for just routine monitoring of flows to smooth the data. To understand what's really happening in terms of patterns over time, and characterize the normal variation, okay, around the smooth patterns. Okay? Because if you can't quantify normal variation, how can you even imagine considering trying to detect subtle changes in the underlying patterns? Okay? So it's not specific to internet data. It's any kind of network problem where you're counting objects moving from node A to node B in whatever context it is. And so if you've got a network of n nodes, you've got the outside world as a node, so you've got n plus 1. You've got an n squared kind of problem. If you want to build models of the complexity of the structure of time series of flows between nodes. So it's a very natural context to want to think about decoupling and recoupling in some sense in order to scale with the number of nodes. The time frame is important too. The data we have here is tick by tick. We're modeling the data in the example on a 30-second intervals. Which is more than enough for the analysis, the decouple analysis. But if you go to shorter time scales, some of the things you can do are going to be challenged, particularly in terms of scalability with the size of the network. So there's a dimension there that is still open to interested researchers. Okay. So we'll be talking about very simple models, conditional Poisson models for count time series. We'll be talking about decoupled simple univariate models. I'll just give a first example to really set the stage and then mention more general dynamic generalized linear models, the models that are more flexible and more interesting. And I'll talk a little bit about the emulation ideas in the context of the example. And depending on time, I've got some slides in there that are on sort of general monitoring questions and Bayesian decision guided automated analysis to detect anomalies. Just very basic, old style sequential tracking. Okay, so MaxPoint used to be a company in Research Triangle Park. It was actually a Duke startup. Inherited some people from a couple of other companies, but then it's been a rich source of interactions and job opportunities, internships for people at Duke and other universities. It was one of the first serious internet advertising companies. So the collaboration that nucleated this and the data that comes in the examples came from MaxPoint. One of their major clients was the Fox News Corporation. And they're in the business, the company, one of the things they do is put ads on web pages. And they run auctions to put those ads on web pages. And so it has to be, any analysis has to be thought about in the context of doing things in parallel on lots of nodes and fast. MaxPoint was bought out by Velasys Digital last year, so we collaborate with Velasys Digital now. They kept most of the people. Lost some money on the MaxPoint stock, but that's a separate issue entirely. Okay, the data, we're not talking about feeding in specifically to the sharp end of the business here. We're talking about just statistical thinking about monitoring flows that helps feed into potentially many kinds of questions in this and other areas. For example, we'll have some examples coming up with some pictures of a network. This simple example here will be 21 nodes. The second example is 220 nodes. So you're interested in all possible pairs. That's a lot of time series. And the network is subdomains of the Fox News website. There are lots of web pages, and they're categorized in various ways. And we'll talk about web domains as nodes in the network. For example, a domain is leisure. Another domain is travel. Okay? And if you see an uptick in travel, people visiting to the domain leisure towards travel, then you might want to put a bit more money quickly into auctions of ads from various companies, like hotel chains, car hire companies, and so forth, to pop up. Okay, so that's the general sort of area of interest in the application. Here's a picture of the network, or a network, the set of 20 nodes. I don't know how well you can see that. The nodes are labeled by number. This is home page, politics, US, opinion, categories defining subdomains. Each of those numbers has a colored circle around it where the density of red indicates occupancy. Numbers of IP addresses currently at that domain. The arrows indicate in this tick, this 30-second tick, the traffic flowing from one node to the next. And the density of black on the arrows you can't really see. You see some are a bit grayer than others. The more blacky, the more gray they are, the more traffic is flowing in that 30-second tick. So that's the raw data. Each IP address has more data. And these companies in principle can identify you. Okay? Our data comes from the East Coast US. And in principle, there's information in the data set that can break it down to a very fine level. Okay? We don't have that data. MaxPoint, Velasys has that data. There are 22 nodes there, and there's a catch-all node, and then there's the outside world, which is node 0, because people come into the website at some point, at some domain, and then they leave the website at some time, somewhere. So we're interested in watching flows, and if I click this, yes, I should say, there's a lot of pre-processing of data that has to be done to define what the counts are. These are 30-second intervals, and if you're on a web page and you click it a few times and refresh, you are known to be still there. And if you go silent for 2 minutes, you are listed as having gone, okay, presumably to the outside world if you didn't show up, your IP address didn't show up somewhere else in the network. As you look through time, that's the next 30 seconds, that's the next 30 seconds. You see some changes. I don't know how clear it is at the back with these faint arrows, but you see some arrows disappear. That means there's no traffic from that node to the node where that arrow was in that instant of time, that 30-second instant. The density of gray on the arrows changes, and you can see things come in and out. This edge just appeared down here from, obviously, a fairly sparsely populated node. It doesn't have much red at all, or even yellow. And then somebody went there. Okay. So some of the data is sparse. 0 counts. Right? We're not going to be addressing that much today. In terms of advertising, the talk tomorrow is in a similar kind of world in terms of models, and we'll be developing more novel and more extensive classes of dynamic models for non-negative counts, where treating 0 especially is very important. But we're not doing that here. Okay, so just to set the theoretical stage, let's look at a node I at an instant in time t, it's our 30-second instance, and label the outflows to other nodes as x's. Okay. So the first index is the node of departure, and the second index is the receiving node. Okay? Xijt is the number of packets, or in this case IP addresses, moving from node I to node j in that unit interval. Okay? Obviously depends on who's in that node to begin. Inflow means inflow to the whole network from the outside world. We'll call that node 0. Outflow to them from that particular node I to the outside world. Okay. So Xijt are the raw bits of data, the time series, doubly indexed by I and j for each pair of nodes. From instant t minus 1 to t, well, if you start with 100 IP addresses and 50 depart and 49 come in, you're down to 99. Okay, so the ends here are the occupancy in terms of the integer counts of IP addresses indexed by time t. Okay. Everybody got the picture? It's just the basic set. So let's look at the very simplest possible BDFM, Bayesian Dynamic Flow Model. I'm going to take that same picture and just trim it down and say, well, let's talk about traffic coming into a node. I'm not going to be talking about a node or a pair of nodes. Okay, we're starting off decoupled. We're not going to be modeling dependencies across pairs of nodes. Not yet. We want scalability. We're going to need a computational load that is no greater than the number of pairs of nodes. Okay. So the first class of models, and the references will be at the end, of course, are just conditional Poissons, where there's a rate of inflow to each node, Poisson mean, but maybe time vary. Well, I mentioned it was on the earlier slide, but I didn't mention it. The data, got several, in the example, several days of data, a period in the morning, a period in the afternoon on each day. And there's some interest in day of week effects, morning versus afternoon effects, but also within each period, looking for differences, new things, anomalies. So this is a canonical model. It has a particular form. It doesn't allow for zero inflation, for example, so that's something we'll talk about tomorrow in a different context. But it's a starting model. And the very first model that we're going to talk about is grafting from stochastic volatility, the simplest model I know for a time evolving Poisson rate. And others in the audience I know have used these models in different contexts, which is a random walk. Okay? So this is a multiplicative random walk. The expected value of the rate at t is what it was at the rate of t minus 1, conditional on that rate of t minus 1. This, in the stochastic volatility literature, this is a context which involves what is called a gamma beta random walk. The random quantity nu t here is a multiplicative innovation in the random walk that has a scale beta distribution. Okay? And this has a nice theoretical structure that allows you to calculate, as you move through time, filtered posterior distributions for the phi t that are gamma distributions. Okay? So that's an important point, and that's one of the reasons we started with this model, because that's analytically trivial. Computations are trivial, and if you can do that for every node, then that's a start on the computational tractability and scalability track. So this is just a model that doesn't predict any direction of change. It's just a random walk. It's saying let's monitor the data and adapt to it. Okay. And the phi's are latent. It's a hidden Markov model. We're going to see some flow numbers x. So it's a starting model for monitoring and therefore smoothing by estimating the trajectories of these latent phi's. Mentioned discount factors a few times. You want to structure this model. Some of you know, some of you don't. A single discount factor will structure the model. It may be node specific. It may be time specific. Okay. We may imagine that there's a greater degree of variation in the underlying rates at a particular time. Everybody gets up, has a cup of coffee, they go to their computer, and they float to the politics homepage yesterday morning. Instead of coming to my talk, they wanted to see what was happening about the Mueller report. All right? So you're going to see a change. In that case, you're going to expect an increase. But you've got to allow for change as well, and discount factors do that. So here's a couple of pictures just to give you the idea. There's some underlying process, phi t, for each node that may be very flat and constant, or it may just bump up at breakfast time and then decay, or it may be rather unpredictable. And that is part of the characterization of normal variation. Poisson variation on top of that is the second part. So simple models like this that ignore relationships across nodes, we're just looking at inflow to the node here, have these nice attributes for scalability. Decouple analyses, you can look at training data and optimize parameters if you want to. I mentioned choosing things like discount factors that define rates of change, or hyperparameters that structure those discount factors as time variable. You can do that in a variety of ways, including marginal likelihood, and discounted marginal likelihood, and other things, because it's all simple analytic tractable. I mentioned that from the stochastic volatility literature, this model's been around. It's the first volatility model ever published in the 1980. Forward filtering of Poisson time series, conditionally Poisson time series with the time varying mean for that Poisson, according to this model. The forward filtering distributions, what you think about the process at time t, is some kind of distribution. Predictive distributions are negative binomial. So you can filter and forecast. And then if you want to look back in time, we haven't talked much about this so far because we've been more focused on forecasting. You want to look at what was that process over time historically in the past. That's called smoothing or retrospective analysis. You've got to be able to say, well, back 2 minutes ago, this is the gamma posterior I had for phi, but I've got more data now. What does that imply for an updated posterior? And in general, the posterior for the full sequence of phi, the trajectory over time, is something that is easy to directly simulate in the exact full joint posterior distribution. So I'll give you some pictures of some examples of that. Again, it's simple computation, trivial computation, direct simulation. As an example, this is data flowing in from the outside world to this leisure subdomain. It's on one day, one of the chosen days. I think this was in the morning. These are the counts. You can see this is from about 10 to 30. The crosses are the counts. The black line is one step ahead mean from the predictive negative binomial distribution. And the interval is some interval, can't remember exactly, predictive credible interval. So tracking phi through time, monitoring the process and smoothing it sequentially online, gives you this picture. Let's suppose it's 95% interval. Okay, that's what we think at each time as we're going through time, pointwise. And then when you look back over time from the last time point and say, well, what really happened, you can see why we call it smoothing. Okay? Because now we've got double-sided data to infer phi at each time point, not just the one-sided data from the forward analysis. Okay? This is a pretty stable trajectory. A little bit high at the beginning and it falls off. Here's another example. We'll see this example a couple of times where the model doesn't seem quite so good, at least as implemented. This is this domain where there's a fairly high intensity of traffic generally. And then mid-morning, it cracked up quite a bit. And the model adapts, of course, but is slow-ish to adapt to that sort of uptick. It had been fairly stable to that point, and therefore the ability to adapt needs probably some change to the model to allow more rapid response, or an extension of the model. The online posterior and the filtered posterior, you see that, you will remember the last slide, the intervals were somewhat wider in the last slide, simply because the count level is much lower. This is a much higher level of counts, so you have more precision about the mean. Okay, so this is smoothing dynamic flow model node by node. Okay, as I mentioned, we'll come back to this. Model ain't that good in its response some of the time. Okay, now let's move to the transitions within between pairs of nodes. That was just stuff coming into the network. Let's look at node I and choose a node J and apply the same reasoning. Let's forget about the fact that we've got a multivariate system. Let's just pretend we like decouple, and we're just going to model each pair separately. Okay? Well, inherently it's different because at this instant, you know how many IP addresses are in this node. Okay? So from flows from this node, you know the maximum that can flow to any other node. And the other nodes, of course, include the outside world. So it's inherently multi-node. There's some instantaneous probability. I'm calling theta here the probability vector. The example, this is 22 dimensions. That is indexed by the node that is transmitting the IP addresses. And the cells in the multinomial, of course, are the receiving nodes. And the time variable. You all know multinomial has a particular structure, and particularly as you get higher dimensions, as you got more bins in this multinomial, building priors and here dynamic models for multinomial probabilities requires some thought. Okay? Do some transformation, build a linear model, something like that. Well, do that, you're going to be out of the ability, away from the ability to do things fast and analytically. Okay? So wouldn't it be nice to do something such as we already did with the inflows? And of course, we all know that multinomials come from Poissons. When you add up independent Poissons and condition it on their sum, you get a multinomial. Right? So there's just a straightforward start on decoupling of multinomial time series by recognizing that and saying, hey, I've really just got 22 conditionally independent Poissons going on here, but I've got to figure out how to deal with the fact that I know what the sum of these flows will be. Okay. Completely analogous to contingency tables, log linear models and other things, where you can model multinomials in various ways by conditioning on row column totals or the full table total or 7 away arrays, various totals. And then you have to think about how to make sure the analysis deals with the fact that the original data constrain to the multinomial n. And I've already got that implicit. You probably can't see this is in a different color than the phi. I've put a number in there, a positive number, indexed by both the transmitting node and time. Because the construction of a multinomial from independent Poissons doesn't know scale. Okay? You take any set of phi's and any set of positive n's and take a set of independent Poissons like this. Okay? Constrained so that the total of the x's summed over j is n. Okay? Then x is a multinomial, and you don't need to know what those n factors are. They disappear in numerator and denominator. Because the probabilities are based on relative rates. Phi 1 divided by phi 2. It doesn't matter what n is. So you've got to choose m, or treat it as an uncertain parameter of some kind. And in this case, it's slightly inspired by contingency tables, but not quite the same as usual in log linear modeling. It's really obvious what m should be. Oh, has this died again? Ah, okay. It's really obvious what m should be. Let me finish the story for the phi's first. Same model for the phi's as we had to begin with the inflows from the outside world. Okay? But they are not anchored on the scale of counts, that are there at time t at node I. Okay? They're just basically on some undetermined scale. It's only their relative values. But you can play the same model out for those, again on pairs of nodes in a completely decoupled format. And the sort of obvious way to choose this scale, because you need one, to run those models decoupled in parallel. This is an evolution model in this state space model. So the m's are really important in terms of how the prior for phi gets updated to a posterior. And this gives it the scale. This says, think about it like this. Suppose this node currently has 50 IP addresses. That's the time t minus 2. Okay? And we're transmitting out to these other nodes according to this multinomial probabilities. Okay? So the phi's there are conditional means relative to counts that are no less than 50. Okay? Let's suppose something happens. There's some news outbreak, and that 50 becomes 500. You have a factor of 10 increase flow into that node in the next time interval. Okay? Well, this then says you've got to multiply these underlying rates by 10. Okay? To keep the definition and the interpretation of these rates anchored to the actual flow rate level. Again, similar things get done in contingency tables and in the use of Poisson regression models, for example, in spatial statistics, where there's often an offset term in a Poisson mean to adjust for the population of the state, for example, or other factors. Other than that, the same sort of ideas apply. The transitions then, which are inherently multinomial, can be modeled in this decoupled way as a set of Poissons. And this is true for every node. We can do it independently across nodes. Okay. So we get the same desirable properties from the point of view of scale. Okay. Filter forward in time, conditional distributions for the phi's or gammas. Filter backwards in time, you can simulate trivially. From the filtered forward in time, the gammas, you can translate and get Dirichlet posteriors for the multinomial probabilities, or you can just simulate them. And moving back in time, you just do the calculation to get posteriors back in time for the transition probabilities. Excuse me. So a couple of examples. This is all 6 days, February and March 2015. These are morning flows. This is an hour period in the morning. looking at I equals 1, the homepage. Where are people going once they're in the website? Through the morning. Okay. So these are the just posterior smooth trajectories of theta I j t. So the conditional probability at time t of moving from homepage to the outside world. So people came in, then they left the website. Looked at the headlines on the homepage, didn't like it, went to see it. Okay. Or they looked at the web page and then the cat knocked the coffee over on the keyboard and they went somewhere else. So through the morning period, this increases, people get up, there's increasing traffic, but these are all on the same scale. So you can see a day-of-week effect. So if you want to think about using models over a period of time and extending this and implementing it, you probably want seasonality.
So what are the 6 plots? What are the 6 plots?
6 different days. Day-of-week effect.
How about the 7? How about the 7?
That wouldn't be aesthetic on the slide. Here's another one. This is this is leaving the website. You see, people come in at breakfast time or coffee time before they go to work, and then they get out. Okay, they go to work, or they take the kids to school, or they clean up the mess that the cat made. This is the same thing to a different web page domain, entertainment. Well, who goes to look for entertainment between 8 and 9 in the morning? Okay, it's fairly stable, or it's decreasing. But again, there are differences. So there are day-to-day differences. There are clearly day-specific effects. So at a more highly aggregate level, or in real time where you know the day, you probably want to take that into account in a more extensive model. The differences here, you can't see the index here. This is the 23rd and the 24th of February, okay, which is Academy Award week. And what you see there is higher levels in the early morning than on the other days, typically. And this is really high. And so part of the interest, is not just what was it, but why? Why might it have been like that? And catching that early enough in the hourly period to then push a lot of ad auctions out on that particular set of pages. These are nice, all very smooth. You might imagine that if you wanted to extend this model, that within a day you might want to build on information you have to do something other than saying this is a random walk. You anticipate an increase and then a decrease. Okay. So these models are just smoothing models to begin to monitor and smooth out conditional Poisson noise with an underlying time-varying rate. And so far, it's all decoupled. There's a lot of data. You saw the narrowness of these intervals on some of these pairs of nodes. Others are much faster. There are many pairs of nodes for which there are periods of no traffic. People don't go to gardening websites and web domains, at 8 o'clock in the morning. Well, some people do. Most people do. Okay, I'll come back to the monitoring and intervention ideas. We're going to get some slightly more elaborate models first and talk about the emulation idea. But this is a first start, and the first paper I mentioned is the JASA paper a couple of years ago. Basically, is built on these models. And one of the co-authors is sitting in the back row, Caro Iri from the University of Tokyo. You're talking this afternoon, Caro. Okay. On something different. Okay. Well, let's be a bit more realistic, and I'm just going to introduce dynamic generalized linear models. I don't know, did you do this for the students in the tutorial on Wednesday? Mentioned it. Okay. Well, I'll mention it again. And then I'll be using them in anger tomorrow, so I'm sort of reserving the stories there for the models more in a different context. Okay. So that was the example I showed you earlier of homepage to world. High levels of flows, and the data are like this. There's this big upsurge for whatever reason. Wouldn't it be nice at this point to feed forward some information into the model if we were anticipating an upsurge? And then there's some sort of leveling off. But obviously the model is not doing a good job. This is one-step forecast intervals. And it's slow to react. And this kind of looks as though a different model might be more useful. So let's get a start on different models. DGLM, dynamic generalized linear models. So take your favorite generalized linear model and put a T on all of the parameters. That's all it is. Okay? A regression model with potentially time-varying regression effects that can allow for feed-forward predictive information. We know the Academy Awards is tonight. We're going to see an increase in traffic in the entertainment domain tomorrow, and probably the day after. Okay? We know that Bob Mueller's report was coming out yesterday morning. We're going to see increased traffic. I mean, who didn't go to, your favorite website to find out about that yesterday morning? I like it. And trends, seasonality. Well, we're talking regression now. Okay. So the BDFM, the bigger class, says, well, let's use dynamic regression, but maintain the decoupled notion because we want to maintain this scalability. So backing out really to the first bullet from yesterday on wanting more elaborate, flexibility, customized, decoupled models. So just one slide on the plus on DGLM. I've dropped the index I and the index J just for clarity, because this is just a general DGLM. So MT is some known scale factor that deals with this relative occupancy issue, or in spatial statistics and epidemiology, relative variation in relative susceptible populations, for example. And phi t is then some underlying latent, hidden state. So a dynamic generalized linear model is one dynamic generalized linear model is a logistic regression. You can take your favorite link, take your probit link, where f is some known set of predictors, and the state vector now is the parameters, the state vector, just like the last few talks, has some evolution time. And in our example, well, I'll give you the example in a minute, right there. For example, simple model. If f is like this for some set of known variables z sub t, so these would be node specific, possibly node pair specific. Okay, an Academy Awards predictor, or a Bob Mueller report release predictor. It could be, you could have more than one z, it could be a vector, but this is just a single scalar predictor. If you take f like that, and you take g like this gives us a dynamic regression. The third element of theta is the dynamic elasticity, the regression coefficient of z sub t, which may time vary. Zt might be a sequence of indicators for just a transient effect. And the constants, ones and zeros in f and g here, you see g as constant, give you the interpretation of the first element of theta as the current, it's not really level, it's intercept in that regression. And the second element as the change in between time t and t minus 1 in the intercept. Okay? Sort of like the intercept and the gradient. So we call that a local linear or linear growth model component. Okay? And these would be time varying too. So go back to that picture where I had an arrow that sort of looked linear. Let me go back to it. This looks like a straight line, 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 a straight line. Okay, so a linear growth model says the slope and intercept are sort of slowly varying. Okay, and it allows you to adapt to slow variation. And that model that I just gave as an example says that you're expecting change in the intercept and slope, but not predicting its direction. So again, it's a smoothing model. Okay. Just an example of a dynamic generalized linear model One important example, and we'll see how important this is in the examples tomorrow in a different context, is to deal with Poisson models not capturing high enough levels of variation that are really unpredictable, over Poisson dispersion, if you like. Bursts now and again of higher values that are just too far out for Poisson. So another model would add a fourth component in here, make theta t a 4 vector, would add a 1 in the f vector at the bottom, and would add a row of and column of zeros to G. Zeros. So this would be a 4x4 matrix with zeros in row and column. Okay? And this then says that the fourth element of theta t doesn't depend on what it was yesterday, because that fourth row of G is 0. It picks up the fourth element of the innovation, okay, time t specific, and I've just called that lambda t. So this is a random effects dynamic generalized linear model, where each day can have this additional random effect, which just adds variation. And then you posterior analysis, forward filtering, backwards sampling, to look at historical trajectories, allows you to interrogate those random effects as well. You might see most of the time they're 0 for one example, but then you get a burst of them for some reason. And the model is capturing that. It's not explaining it. And importantly, in that kind of context, by capturing it that way, the inference on the level gradient and the coefficient of z would be protected from those wild bursts of higher counts. Often we just sacrifice description in favor of a statistical empirical representation, but it often has those positive benefits. Okay. So dynamic generalized linear models, it could be binomial, it could be gamma, any exponential families of dynamic generalized linear models. These have been around a few years, 35 years or thereabouts. So now we're outside of conditionally linear, conditionally Gaussian. We're outside a simple volatility beta gamma model for which the maths for which analysis is all analytic. And we rely on very venerable approximations where the forward filtering and retrospective smoothing are based only on the means and the covariance matrices of the state vectors. Okay? And there's a phrase linear Bayes that tells you what the Bayesian decision theory rationale for that is. And in forecasting, at each time, remember we've got the evolve step, so you evolve means and variances. And we've got a forecasting step. Well, we want to have relevant forecasting distributions. And then we see the observation at time t, the conditional Poisson. We want to do the update. If we constrain the distribution of the Poisson rate to be a gamma, consistent with the mean and the variance for the state, then we get negative binomial forecast distributions. And we get conjugate updating to the posterior that then feeds into the linear Bayes update of the posterior mean and variance matrix for the state vector. In a nutshell, it's kind of like the normal model where these calculations are exact. But there's a combination of what we will nowadays call a variational Bayes approximation and a linear Bayes approximation. Because otherwise, you're stuck doing some nasty Monte Carlo, Markov chain Monte Carlo or something like that. They're very well tried and tested and very, very accurate approximations. Critically, it maintains faith with the desiderata that underlie the ability to scale. Okay, so there's a class of models then. Excuse me, my friends need a drink. Okay, so what? So, classes of models which have some predictability. Bayesian dynamic flow models which allow regression components, trend components, seasonality components. You can see how it could be elaborated. Inflows could consume various predictive information. Outflows between node flows. all decoupled, all fast, all scalable according to the n choose 2, where n is the number of nodes. But no elaboration or description or interrogation of relationships across nodes within each time point, other than the outflows between pairs. So let's get into that a little bit. This is the recouple stage. At each time point, we know where we are in terms of posterior distributions for the parameters and states at that time point. We can look back in time, we can forecast. We can simulate those posteriors, whether filtered or whether smooth. So now let's ask questions about, well, tell me more about the temporal evolution of relationships amongst nodes and node-specific, quantify variation over time in node-specific characteristics. We've got to start thinking about how these sets of multinomial probabilities and the inflowing Poisson rates interact, how they relate. And the class of models that, one class of models, it's actually the only class of models for this problem, I think, is what we'll call a gravity model, dynamic gravity model. Has anybody heard that term? It's got nothing to do, well, it's got nothing to do with physics and gravity. It's an important class of models historically in transportation network flows. And it's being used a lot and more. There's been some interesting Bayesian work in the last several years on using it in looking at infectious disease transmission, where nodes are communities. Okay. So what is it? Let me introduce the gravity model and then show you how, with this decoupled system of Bayesian dynamic flow models, we can do inference, full inference, in this much more complicated, challenging, from a point of view of fitting the model, class of gravity models. So this is our story. Inflow to each node is Poisson. Transitions from a node to other places at each time are conditional multinomials. Right? That's what we have. I'm putting that there just to remind you of the labels on the various parameters. Okay. More generally, this is a different Z than before. It could be a very large number of things that you might know about node I. Okay. We're using particular models here, but there are lots of other things that we could use in bigger models for these states. Here's a representation of rates of flow from node I to node J that basically is as general as possible. They're positive numbers. So each of these, the mu's, the alphas, there's one mu at each time. There's one alpha for each node at each time. There's one beta for each node at each time. And then there's a gamma for every pair of nodes at each time. Okay? These are some positive numbers. Any model you write down for this matrix phi ij's evolving over time will look like this. Okay? There's no generality lost because I can put anything I want to in these sets. So in terms of thinking about relationships amongst the states that we're sort of identifying through the posterior distributions here, across nodes, across the whole set of nodes, we'd be interested in a model like this. So think about this as a main effect, mu, intensity of traffic in the network. Alpha, indexed by node I, as an effect influencing the outflow rates from node I at time t, a main effect. Beta, indexed by j, influencing the inflow, the attractiveness of node j over time. Another main effect. Okay? And gamma, an interaction. And we use the term, we'll introduce the term affinity for the gamma j. It's an interaction between node j, node I, and node j. And if it's big, they're all positive. If it's big, that's going to increase phi. So there's going to be more of a flow in that instant from node I to node j. Whatever the main effects alpha I and beta j may be. Okay. So gravity model comes from the literature. I mentioned transportation flows and epidemic spread. I'm trying to remember the name. Peter Cogden wrote a series of papers about 10 years ago. And he was interested in Bayesian analysis of gravity models. A model like this for epidemic transmissions, where he had some simple log linear regression. Okay. And it's really just an elaboration of a 2x2 contingency table, okay, when there's no time varying element. And the alphas, betas, alphas are row effects, betas are column effects, and the gammas are interactions. Okay. There's a history to the term gravity. If you have covariates in here, from the transportation literature, but that's the only reason we use it, because that's a good literature for this work to contact. I wrote a paper. This is an unpublished Duke and NIST, National Institute of Statistical Science report, just a couple of years ago, when Gabrielle was a student, on that distant galaxy, where we had 900 nodes. It was transportation in the Chicago area transit system. The Chicago area is chopped up into 900 zones. This is 1994. Big gravity model, big MCMC. The reason it's unpublished is that I went on sabbatical for a year and got distracted. But if I were to revisit that, I'd want to let the MCMC run for a few more days. And that had no time element in it, okay? Okay, so here's the first dynamic gravity model. The first time gravity models have been published with time-varying parameters. So I've described one way to think about what these guys mean. There are no z's there now. I'm just saying, if I know the phi's at time ij, at time t for all pairs I and j, and I have this representation, okay, can I recover these parameters of the gravity model, the alpha, the mu, the alpha, the beta, and the gammas, from that information? Because I know I can fit those phi's properly in my dynamic flow model, decoupled flow models. If you try and fit that model, you have to first complete it. You have to make some assumptions about how these alphas, betas, and gammas vary in time. If you were to fix them as constants, you can then go ahead and use whatever numerical methods you want for contingency tables. If you want to have them time varying, you can make up some models. You take log linear, dynamic linear models. But to fit it, because of the products, you're going to be stuck, because you have to fit it to the n times n dimensional set of nodes. Okay, the n times n dimensional parameter space defined by the full multivariate set of nodes. So we're not going to do that because it's impossible from the point of view of scalability. We're going to do what I just alluded to. We're going to say, run these models to learn about these things and then figure out what these mu's, alphas, betas, and gammas might be. Okay. So this is a different technical use of the concept of recouple. Okay. But it's the same conceptual tautology. It's the same conceptual concept. It's taking a set of decoupled models and enforcing the full multivariate structure on them. Okay? So the Bayesian dynamic flow model is the dynamic gravity model. Okay? I want to map between these models. Well, we know in contingency tables that you either have to be prepared to say, I don't care about identification. Bayesians do that a lot. Or more traditionally, use aliasing constraints to enforce identification. Okay? On the log scale, you've got a sum of main effects for rows and columns, and then all of the interactions. Okay? So you've got to have some zero-sum constraints or some other sum constraints to enforce that integration. And that translates zero-sum on the log scale, translates to geometric means being 1. Okay. So the alphas have to, product of the alphas is 1 across all nodes, product of the betas is 1. The products for each node of the interaction with all of the other nodes has to be 1. So the interactions are constrained. Okay? Oops. And then if you put those constraints in, and you look at the system of n-squared equations at each time t, you can do the inverse. And I love this symbol, but I don't know what it's called. This stands for geometric mean. Okay. These constraints show you that if you just take the geometric mean over all I and j, you get mu. Okay? So it's the overall average, right? You do the row column geometric means, you get the alphas and betas. Okay? And then when you've got all of those guys, what you have left is the interaction. So if I know all of the phi ij's at a particular time t, I can calculate the parameters of the graph. If I believe that I've got a very flexible set of decoupled Bayesian dynamic flow models to provide reliable inference through posterior distributions on the phi ijt's over time, then I can do the transformation to the graphical model parameters. And in particular, if I have direct posterior simulations of the phi ij's over time from these completely decoupled, completely analyzed in parallel models, then I just simulate them and apply this transformation. And that gives me posterior distributions for the parameters in a full two-way layout, full, all main, all effects, and all interactions. Okay. So the concept, we use the term emulation. Okay? Emulation is used for a variety of purposes in statistics, and within Bayesian statistics we had it at least once today from Gabriel in his talk before lunch. This is emulation used in a slightly different sense, and there are a number of examples of this, where you've got a model you want to fit and you can't fit it. Well, you could probably fit some version of it, but if you're going to scale it and you want to roll it out on a 2,000 node network, forget it. Forget it. So there's a model that is challenging to fit, and it's certainly challenging to fit if you want to do it faster in time. Here's a model that's trivial to fit, the decoupled set of equations. So we're emulating in this analysis. For some purposes, this is all you stop here, you're done. But depending on your goals, and here our goals are to interrogate the structure of relationships, how they vary in time, in more depth. And we'll see some examples of that in a minute. Then this simple model becomes an emulator of the target model, the dynamic graph. So a few examples. Here's one of the mornings. And what I'm showing here is what we're now going to call the outflow parameters. The main effects alpha I, okay, for each node I, represent intensity, contributions to the intensity of flows out from that node. Okay, so here we're coming from, this is home page. The red dashed line is 0. This is alpha over time for home page. And the little crosses there are data when there was some outflow. Some of these sets of crosses that you don't have one every tick because we just didn't plot them when they were 0. Okay? So the outflow from the home page, it's up there at a level 15. Now this is some kind of relative level. Okay? To reflect. Because there's an overall mean, the mu t. Okay. And this is saying all other things being equal, the outflow from the home page domain is 15 times higher than average. Average is geometric mean of 1. This is politics. People come into politics. This is 1.1, 1.2. Later in the morning, they get out. Okay, there's an increase, a slight increase, a 10% increase in the later morning period. This is opinion. It's above 1, pretty surely here, but not so much. Entertainment's fairly constant, 2.25. So people do go to entertainment more than on average across the set of 22 domains in the morning. I don't know, but people watch on TV between 8 and 9 o'clock. Or maybe they want to find out what happened on Hollywood last night, what the latest scandal is. I don't know. I don't. Has anybody ever been to the entertainment pages on the Fox News website? Well, I know the answer to that is yes, but anybody here remember? I don't know if I've ever been there. Science, 0.75, pretty constant. You know, quite a few of us probably look at scientific news, right, after breakfast, but in general, it's not so heavily subscribed. Okay. And here's World. This is a collection of miscellaneous things, a collection of miscellaneous websites, and this shows that 1.2 to 2. There's increasing interest in what's happening outside the world among the consumers of that start at the homepage or are there in the early morning. Okay, so people go and look for. Well, they see some news about I don't know what's happening in Argentina now in terms of the inflation and then, oh, but there's some bright spots because the tourist industry is beginning to rise and there's some really good deals, okay? So everybody then goes to the Argentina page. Okay? I don't know what it is, but it's a change, okay? So the flow models are monitoring the transition probabilities across pages, but this is an overall intensity of flow from the home page towards that particular page, okay? The beta J, so these are the attractor contribution main effects. How attractive node J is relative to the average attractiveness. Okay, so it's the second dimension main effect. Our home page, that's at about 14. So it's an attractive domain to go to. 14 times the average across the network. Politics 1.1, pretty stable. Opinion, a little bit more attractive than average. But then people go to work and they've had enough of opinion. Entertainment, look at that, 2.2. Okay, I hadn't really noticed entertainment before. Science is not attractive. About half as attractive as, or 3/4 as attractive than the average, and world is attractive. Okay? So we can look at main effects. There's lots of nodes and lots of interaction effects. I just wanted to put this up. So I showed you a few of these and a few of these. The reason I put this up is to show you that there's sort of clustering of behavior. And so the main effects themselves, say something about the particular node as a provider of traffic or a receiver of traffic and how that varies in time. But also, the patterns can be shared. It's really a hierarchical system, right? At the bottom, you've got web pages, and these domains can be clustered in various ways. This is really just showing that. And there's more diversity of I'm sorry I didn't give you a scale here. It doesn't really matter. So yellow is higher, blue is lower. Okay. So let's look a little bit at these interactions. Because it's really where the interest is in this more structured gravity model. Here we are on February the 23rd in the morning, and we're looking at flows from homepage to science. Okay, we've already pointed out that that's not a very popular place to go. Okay. These are the underlying phi's from the dynamic flow model over time, pretty stable. It's up at about 15 to 20. This is the implied conditional probability of time t of moving from home page to science. Okay? And it's down at 1 in 1,000. Okay? It's not a very popular place to go. Pretty stable. So what we have here then are the main effects. This is at about, we've already seen this is at about 15 for the home page, and the attractiveness of science is at about 0.8. Okay? So the main effects are pretty constant. There's a slight uptick later in the morning. Okay, main effects and in and out. And the affinity, I'm using that term for the interaction. So in this case, phi ij is the interaction. So we'll call it the affinity of, which way do we do this? Which way do we do this? The affinity of science for homepage, the affinity of homepage for science. I can't remember which way we decided to put it, but that's the affinity. It's the affinity of homepage for science for the outflows. Okay? So this is increasing over the morning. It's really different, depressed below 1 in the early morning, but later on it's about average. Okay. And later on in the morning, I'm sorry, I should have put the gamma in there. In the late morning, the intervals smack around 0. Okay. So by that time, it's just main effects. But earlier in the morning, people don't like to go to science from homepage. And this picture is just a shaded representation of something Gabrielle Quattro actually sort of got into a little bit this morning, of just a summary of the posterior distribution in a different way. It's saying, take the 95% credible interval, and is the red line inside it or not? What's the probability? So the credible interval is a high posterior density interval. Okay? And then you demark that by the line, the red line at 1, and ask what's the probability in that highest posterior density region. Okay? So it's kind of like a Bayesian, I won't use the term p-value, or significance. It's a fairly standard, but maybe not so standard in this kind of area, summary of whether or not this interaction effect in this case is not 0 on the log scale. And I put that in, and we like that because this is getting into this whole notion of dynamic sparsity, which keeps being mentioned. And in contingency tables, whether they're dynamic or not, with main effects and interactions, you might have more than 2 factors. Here we've just got 2. Origin, destination. You might have several more factors. Often the action is in the interactions. Second order here, or third order, or more. But most of them are going to be irrelevant. Okay, sparsity of interaction effects in multi-way classified data. And here we've got an example of that, where pretty much in the second half of the second third of the morning, that's not an important interaction. Okay, the log of gamma IJT is 0. Okay, pretty much. So in the other period, however, it was pretty important. Okay, I've got the slide on that. But I've just described what it is, and the probability that 1 is inside the highest posterior density region at some level of significance. Just a couple more examples. Well, these 2 examples, we see here a very stable pattern over time. Okay, this is in the gamma. This is a gamma. Let me read this off for you. This is homepage to tech. Very stable, well below average. It's clearly significant, so there's no gray shading appearing. The gray is all at 0. Same story here in terms of the significance of this interaction, but it's a very time-varying interaction. Okay? This is entertainment to other. And down here, a third example, it's a negligible interaction, basically. The gray shading says 95% of the probability sits around 1 pretty much most of the time. Okay? So you can dig into this n-squared set of interactions over time. So we've got 400 pictures like this. Or you can numerically summarize. One of the reasons the numbers here are being displayed is that they give you numerical summaries that you can then prioritize how to interrogate the interactions. my timing here? 5 minutes? Okay. I'm going to skip to the end. Actually, this is just, again, summarizing. Well, let me give you the example because I mentioned this earlier. This is on 4 different days. First two, top row, were right after the Academy Awards. And what we have in red is the overall mean over time in the network, so intensity of traffic in the morning, and in blue in the afternoon. They're pretty similar here. There's an increase in later morning on both of these 2 days. There's a lot of interest in this kind of stuff, and the fallout, the media fallout, potentially. That's why we see a little difference there. This is the 3rd of March and the 4th of March, where there's a clear difference in the morning and afternoon traffic. And we don't really know why that is, but that was the afternoon when we started hearing about hidden servers in the Clinton basement. A lot of news websites saw a lot more action. But why it broke down between afternoon and morning like this, we're not sure. I don't really have time to go into this in detail. Let me walk through this slide and skip the next 2 slides because I'm out of time. And I hate to be in the audience when people go over time. Carlos just left, so he didn't miss it. So, of course, the applied system is not just rolling over time, it's worrying about things such as we saw with one of the examples where the model forecasting breaks down. So here we have an example where we're coming along. These are the observations. The black line is 1-step forecast. The black interval is a 95% interval. Under the predictive negative binomial distribution in the dynamic flow model. So here we get to this point and we say, oh, this guy's a bit wild. Well, no, it's not so wild. Maybe there's a little bit of extra Poisson variation. We could deal with that. Is it something we want to worry about? Should we throw that observation out and then go on a bit longer? Or should we change the model? Or should we just leave it and see what happens? Okay. Well, you might decide to leave it and see what happens, and then the next tick, you get that point, and you think, that's sure, maybe I should have done something. Maybe there's something going on. Maybe I should change the model a bit, or try and figure out why the rate seems to go up a little bit. Or maybe just leave it. But it's the suspicion that might make you want to think, well, has the level jumped up a little bit in an unpredictable way? If it has jumped up a little bit, is it going to jump up more? Or is it going to jump down again? Okay. So it raises uncertainty. Okay. And one response to just that is to say, okay, well, let me accept that I'm in a raised state of uncertainty and take my current posterior distribution for the underlying rate and make it more diffuse. Okay? So that if things are changing, I'm going to be more adaptable. That's a bad idea if these two turn out to be outliers. Okay? So let's suppose we choose to do nothing, and then the next 2 ticks become sort of confirmatory. There's been some kind of upward shift. We're not tracking that drift upwards. So at that point, you probably want to jump in and do something such as I described, or something more elaborate. Okay? If you don't, then you see the picture. It's only half the interval that I showed earlier, that you will be underestimating the drift up. Okay? I'm not going to go through this slide. I can give you references. But just to illustrate it, the effect it has, this is just standard sequential Bayesian monitoring and tracking predictive performance in a decision theoretic way. Okay? It has some very nice features, very simple to automate and implement. I was once accused of inventing the first Bayesian pure significance test. The methodology that underlies this has a bit of that flavor. But I was accused of that, and I never called it that, and it's not that. But anyway, so here we're coming along with that data, and the crosses are the data, and then the circles I've just circled as interesting points because they were less well predicted in the sense that I just described. And then the little stars cover the points where the intervention was called for. And just intervening to make things more uncertain in terms of the current understanding of what the states might be. By making those more diffuse allows you to adapt more to the next observations. You might want to throw away wild values as well, but you don't want to adapt to wild values. These arrows indicate the points at which some adaptation was made. If you run the model blind, you'll get what is now the red set of one-set forecast means and the shaded orange intervals. But if it's customized this way, you adapt much more rapidly. You're still under forecasting a little bit here. Probably a little more aggressive intervention was needed. But you get the idea. So in terms of simple decision theory guided monitoring and for anomalies, to allow the model to protect the model from outliers and allow the model to adapt more, there's some standard Bayesian machinery that applies beautifully to decoupled sets of univariate models. Another example showing that when it's not needed, it doesn't do any harm. Okay? So that's pretty much it. I'm sorry I'm 2 minutes over. I won't read through the words for you there. There's a decoupled set of models. There's a recoupling to the gravity models, which is different kind of recoupling, and it really is a nice instantiation of this whole concept of building a simple model to emulate a different model that's much harder to access. And there are some things of interest. I'll talk about a couple of these tomorrow. I'll talk more about zero and very low count modeling in count time series tomorrow in a forecasting context, and a few other things that are obvious sort of areas for this kind of modeling work to go. It's a very open area for research for anyone interested. Okay, so I mentioned Karu, who's a professor of economics at the University of Tokyo now, who will be speaking this afternoon on a completely different topic. I have no idea what it is. Ji Chen is at LinkedIn. And David Banks was a partner in some of the early work on here. Here are two collaborators from MaxPoint, no longer with MaxPoint, because MaxPoint no longer exists, and they decided to do startups instead. If you're interested, there's a JASA paper last year, and the paper that's available on arXiv is about to appear in Network Science. With that, thanks for your attention, and I do apologize for the 3 minutes. Thanks for your attention.